Last time we discussed the first law of motion and we discussed inertia, and first law is called the law of inertia. Let's quickly revise the first law of motion. The first law says if an object is not in motion, stationary, not moving, it wants to remain like that. And if an object is in motion, it wants to remain in motion. Unless, कब तक ऐसा रहेगा? Unless an unbalanced force acts on it. So a stationary thing wants to remain stationary, a moving thing wants to remain moving thing until an unbalanced force acts on it. और इसके innumerable examples हमने दिए थे. If I correctly remember and I start counting, I am standing in a bus. The bus suddenly starts. I go back. I am in a moving bus. The bus suddenly stops. I go aage. I am in a car. The car is going at 100 km per hour and suddenly the car applies brakes and my head bangs with the windscreen. Seat belt, importance of seat belt. एक जो हमने नहीं डिस्कस किया था, चालू ट्रेन या चालू बस में से जब उतरते हो तो if you just land on your 2 feet, you will fall. But the minute you climb down from a running bus or a running train, you have to start running with it slowly. Then you will not fall. What is the reason of this thing? When you were in the train, you were moving. जब तुम जमीन पे उतरे और दोनों पैर जमीन पे डाल दिए तो अचानक you are trying to become stationary, but your body is following the first law. The body was in motion, it wants to remain in motion. और बॉडी को आगे जाना है और तुम्हारे पैर वहीं पे अटक गए तो तुम गिर जाओगे. Therefore you have to run for some time and gradually slow down. रनिंग रेस में रनिंग रेस जीतने के बाद भी आदमी दौड़ते रहता है. That is the fifth example that I am running, I want to continue running. धीरे धीरे stop कर सकता है, अचानक नहीं. So there are a lot of examples like this about things are moving and they want to remain moving, like a fan. After you switch off, the fan still continues to go on and on. अब moving an empty box is easy versus moving a box full of books. True. किसमें फोर्स ज्यादा लगेगा? In which thing do you need more force? Moving an empty box, less force is required. But moving a box full of books, more force is required. Kicking a football, a real football, versus kicking a stone of same size. फुटबॉल जितनी साइज का पत्थर को मारने के लिए ज्यादा फोर्स लगेगा, बट फुटबॉल को मारने के लिए कम फोर्स लगेगा. Therefore, can I say that force is related to mass? Box full of books and stone of same size, मास का फर्क है. फुटबॉल के कंपैरिजन में स्टोन का मास ज्यादा है, एम्प्टी बॉक्स के कंपैरिजन में फुल बॉक्स का मास ज्यादा है. Therefore, force is related to mass. जिसका मास ज्यादा होगा वो ज्यादा फोर्स दे सकता है या उसको ज्यादा फोर्स की जरूरत है, डिपेंडिंग ऑन व्हाट यू आर ट्राइंग टू डू. Hold on to this conversation that mass is important. Mass, M, it's a very important thing. Now compare these scenarios. Table tennis ball hits you versus a cricket ball hits you. Same speed पे टीटी का बॉल फेंक के मारू या क्रिकेट का सीजन बॉल फेंक के मारू, फर्क है? ऑफ कोर्स है। किस में ज्यादा लगेगा? क्रिकेट बॉल में। किस में ज्यादा डैमेज होगा? क्रिकेट बॉल से। हु विल क्रिएट मोर फोर्स? क्रिकेट बॉल। क्योंकि टेबल टेनिस का बॉल छोटा है, हल्का है, बट क्रिकेट का बॉल भारी है। मास इज इंपॉर्टेंट। इसका मास कम है, इसका मास ज्यादा है। ओके। Is it easy to stop a moving cycle which is moving at speed of 5 meter per second? Yeah. Is it easy to stop a train which is moving at same speed 5 meter per second? दोनों साइकिल और ट्रेन की स्पीड सेम है, 5 मीटर पर सेकेंड। किसको इजीली स्टॉप कर सकते हैं? ऑफ कोर्स साइकिल को इजीली स्टॉप कर सकते हैं। ट्रेन भले कितनी भी स्लो हो, उसको स्टॉप करना मुश्किल है। क्या फर्क है दोनों में? मास। The train has huge mass, the cycle has less mass. और क्योंकि साइकिल का मास कम है, तो हम जितना दम लगाते हैं उसको रोकने के लिए वो जल्दी रुक जाती है, because it has less mass. But to stop the train, which is huge, we need a lot of force, a lot of energy to stop it. Consider the third scenario. A bullet is thrown with hand versus bullet fired from a gun. What can kill you? हाथ से फेंक के बुलेट फेंकू, बुलेट मारू, या गन में डाल के शूट करूं? बुलेट तो बुलेट है। बुलेट का वजन यहां पे भी 5 ग्राम है, मास यहां पे भी 5 ग्राम है, तो भी बुलेट फायर्ड फ्रॉम अ गन इज डेंजरस। हाथ से फेंका हुआ बुलेट से कुछ नहीं होता, अनलेस रजनीकांत इज थ्रोइंग इट, तो वो बुलेट से भी फास्ट हो, वो गन से भी फास्ट हो सकता है। बट दैट्स नॉट द पॉइंट। व्हाट इज द डिफरेंस इन बोथ द सिनेरियोस? Mass of bullet is same. The difference is velocity, the speed. When you throw a bullet with hand, the velocity is less, but bullet fired from a gun, the velocity is high. So now, in short, when TT ball hits you, it hits you with some force. Cricket ball hits you, some force. To stop moving cycle, you need to apply force. To stop a moving train, you need to apply force. The bullet thrown with a hand still touches you and applies some force on your body. And the bullet fired from a gun has so much force that it penetrates inside your body. साइंटिस्ट ने सोचा कि कुछ चीजों में मास इंपॉर्टेंट है, कुछ चीजों में वेलोसिटी इंपॉर्टेंट है. They created a new thing called P, momentum, and said momentum is equal to mass into velocity. हर एक ऑब्जेक्ट का एक मोमेंटम होता है, and that momentum is equal to mass multiplied by velocity. और मोमेंटम और फोर्स का क्या रिलेशन? अभी तक तो हम फोर्स बोल रहे थे, टेबल टेनिस हिट्स यू विद सम फोर्स, क्रिकेट बॉल हिट्स यू विद मोर फोर्स. तो मोमेंटम आ गया, फोर्स कहां चला गया? That's where we take the next step and understand the second law of motion. Momentum is equal to mass into velocity is a part of the second law of motion. Momentum का सिंबल है P, so P is equal to mv. इसकी यूनिट क्या होगी वो हम खुद बना सकते हैं, बहुत ही इजीली उसकी यूनिट बना सकते हैं. मोमेंटम इज इक्वल टू मास इनटू वेलोसिटी. मास का यूनिट केजी, वेलोसिटी का मीटर पर सेकेंड. देयरफॉर मोमेंटम का यूनिट इज केजी मीटर पर सेकेंड. सिंपल, kg meter per second, which is written here. The SI unit of momentum is kg meter per second. और पर सेकेंड मतलब नीचे होता है सेकेंड, उसको ऊपर ले लो तो केजी मीटर सेकेंड इनवर्स आएगा, केजी मीटर सेकेंड इनवर्स. Since the application of an unbalanced force brings a change in the velocity of the object, it is therefore clear that force also produces a change in momentum. अब जो मैं बोल रहा था कि momentum और force के बीच में क्या relationship है, that's itself the second law. The second law of motion states that the rate of change of momentum of an object is directly proportional to the applied unbalanced force. मतलब rate of change of momentum is directly proportional to the force. This is second law of motion which you have to by heart. This relationship you have to by heart. Now I'll explain you what it is. Change of momentum मतलब क्या? Change of momentum मतलब फाइनल मोमेंटम माइनस इनिशियल मोमेंटम. दुनिया में किसी भी चीज का चेंज मतलब फाइनल माइनस इनिशियल. हाइट बढ़ गई तो फाइनल हाइट माइनस इनिशियल हाइट इज द चेंज. पेंसिल है, पेंसिल लिख लिख के छोटी हो जाती है तो इनिशियल माइनस फाइनल, दैट्स द चेंज. तो चेंज इन मोमेंटम मतलब फाइनल माइनस इनिशियल, दैट्स वन थिंग. बट रेट ऑफ चेंज ऑफ मोमेंटम, रेट मतलब डिवाइडेड बाय टाइम. किसी भी चीज का रेट मतलब डिवाइड बाय टाइम. लाइक स्पीड, स्पीड इज रेट ऑफ चेंज ऑफ डिस्टेंस. velocity is rate of change of displacement. Acceleration is rate of change of velocity. हर एक में अपॉन टी आता है. तो rate of change of momentum is directly proportional to force. This is what the second law of motion says. अब समझो, एक बॉल है जिसका मास है 1 kg और जिसकी वेलोसिटी है 10 मीटर पर सेकेंड. ये बॉल इस डायरेक्शन में ट्रैवल कर रही है एंड इट इज हिटिंग द विकेट कीपर. क्या है? विकेट कीपर ने हेलमेट पहना है. ओके, सेफ्टी फर्स्ट. So the ball hits the wicket keeper. The wicket keeper goes dizzy for 2 minutes and he becomes normal again. Ball was moving at 10 meters per second speed and it has mass. Therefore, it could create force. First thing we can calculate is what is the momentum of the ball. बॉल जब बॉलर के हाथ में था तब उसका मास क्या था? 1 kg और उसकी इनिशियल वेलोसिटी 0 थी. बॉल हाथ में पकड़ के रखा है, इट हैज नो वेलोसिटी, बट व्हेन यू थ्रो इट अटेन्स वेलोसिटी. इस जंक्शन पे मोमेंटम कितना था? मोमेंटम इज मास इनटू वेलोसिटी, 1 into 0, 0 मोमेंटम. बट जब फेंका और बॉल जा रहा था तब मोमेंटम कितना था? मास इनटू वेलोसिटी 1 into 10, 10. And this change in momentum, this change in momentum took place in 2 seconds of time. 2 सेकेंड लगे बॉल के मोमेंटम को 0 से 10 पहुंचने में. From this scenario, we can calculate how much force will be applied on the helmet of that wicket keeper. कितना जोर से लगेगा क्या फोर्स होगा that can be calculated, because force is directly proportional to rate of change of momentum. मतलब difference in momentum upon time. Change in momentum मतलब final momentum minus initial momentum upon time. Final momentum 10, initial 0 upon 2 seconds. 5 Newton force will be applied on the helmet of the wicketkeeper. अब मुझे फोर्स बढ़ाना है. I want to increase that force with which it hits the helmet. What do I have to increase? सोच के बताओ, फोर्स बढ़ाने के लिए क्या बढ़ाना पड़ेगा? फोर्स बढ़ाना है तो ये जो मोमेंटम का डिफरेंस है वो बढ़ाना पड़ेगा. मोमेंटम का डिफरेंस चेंज करने के लिए, टू गेट अ बिग डिफरेंस, आई वॉन्ट दैट दिस नंबर शुड इंक्रीज. ये 10 की जगह 20 होता तो फोर्स बढ़ जाता. तो फाइनल मोमेंटम बढ़ाने के लिए क्या बढ़ा सकते हैं? या तो मास या वेलोसिटी. तो या तो मैं 2 किलो का बॉल फेंकू 1 किलो की जगह पे, दैट इज नॉट पॉसिबल. बट व्हाट इज पॉसिबल इज, instead of throwing ball at 10 meter per second, I increase the speed and throw the ball faster at 20 meter per second. See what happens when same ball was hit at 20 meters per second. Final momentum will become mass 1 kg, velocity 20, therefore momentum 20. Force is proportional to change in momentum upon time. Change in momentum is final minus initial momentum upon time. Final momentum 20, initial 0 upon time 2. Force बढ़ गया, 10 न्यूटन फोर्स हो गया. But there is one more option how I can increase the force without increasing the velocity. एक लिमिट होती है फास्ट बॉल फेंकने की. अगर वो लिमिट क्रॉस हो जाए, उसके बाद फोर्स बढ़ाना है तो क्या करोगे? टाइम घटाओगे. दिस इज बेसिक मैथ्स. फोर्स इज प्रोपोर्शनल टू चेंज इन मोमेंटम अपॉन टाइम. अगर टाइम कम हो तो भी फोर्स बढ़ेगा, बिकॉज टी इज इन डिनोमिनेटर. सो इंस्टेड ऑफ adding extra velocity, I reduce the time period in which that change is taking place. प्रैक्टिकली कैसे करते हैं उसमें मत जाओ फिलहाल. थियरी है ये, तो थियरी की तरह समझना पड़ेगा. So 1 kg ball thrown at a velocity of 10 meter per second, but initially that 1 kg ball had a velocity of 0 meter per second, and this change happened in half a second. फास्ट हुआ तो क्या फर्क पड़ेगा? देखो, इनिशियल मोमेंटम pi is mass into initial velocity. Mass 1 kg, initial velocity 0, initial momentum 0. Final momentum, mass into velocity, final velocity, mass 1 kg, final velocity 10, final momentum 10. Force is proportional to change in momentum upon time. That is final minus initial momentum upon time. 10 minus 0 upon 0.5. 20 न्यूटन. 5 का 20 न्यूटन हो गया. सो फोर्स बढ़ाने के लिए या टाइम घटाओ या वेलोसिटी बढ़ाओ या मास बढ़ाओ. Once again, I'm continuing the discussion of second law of motion. Second law of motion के wordings क्या है? Applied force is directly proportional to the rate of change of momentum. This is the second law of motion. मतलब F is proportional to change in momentum upon time. But F is proportional to change in momentum मतलब final momentum minus initial momentum upon time. ओके, दो तीन बार यूज किया एग्जाम्पल में. बट फाइनल मोमेंटम इज मास इनटू फाइनल वेलोसिटी, इनिशियल मोमेंटम इज मास इनटू इनिशियल वेलोसिटी. यस, वो भी अभी थोड़ी देर पहले यूज किया. कैन आई नॉट टेक m कॉमन? यस, v माइनस यू बाई टी बचा, m बाहर आ गया. बट मोशन चैप्टर में सीखा था दैट v माइनस यू बाई टी मतलब एक्सेलरेशन. सोचो, याद करो, एक्सेलरेशन का फॉर्मूला है ये. एंड देयरफॉर f इज इक्वल टू kma इज अ डेरिवेशन ऑफ सेकेंड लॉ ऑफ मोशन. जो 3 मार्क का क्वेश्चन आएगा या 2 मार्क का, बहुत इजी है, बहुत इंपॉर्टेंट है, इंपॉर्टेंट एंड इजी. derive the formula of f is equal to kma. This is it, and it's very logical. 20 सेकेंड रिवाइंड करो और वापस पूरा सुनो, कॉपी करो और बाय हार्ट कर लो. This is the derivation of formula of second law of motion. And therefore, as I said, फोर्स बढ़ाने के लिए क्या क्या कर सकते हैं? फोर्स बढ़ाने के लिए मास बढ़ाओ, ऑप्शन 1. वेलोसिटी बढ़ाओ, ऑप्शन 2. या टाइम घटाओ, ऑप्शन 3. क्रिकेट में कैच करना पड़ता है. So this is the fielder who is looking at the ball and running, trying to catch the ball, and this is where the ball is. Fielder is trying to catch the ball. He does not catch the ball and stand like this. ये कैच करके हाथ रुकते नहीं है, उसके हाथ ऐसे नीचे जाते. Slowly he takes his hands back. Why is the question? The answer lies in this discussion. कि क्रिकेट में बहुत ऊंचा कैच है, वो पकड़ने के बाद हाथ ऐसे नीचे क्यों करता है? क्यों ऐसे ही नहीं रहने देता? रीजन, बॉल का वेलोसिटी हाई है व्हेन इट इज फॉलिंग डाउन. ये इनिशियल वेलोसिटी है, देयरफॉर वी विल कॉल इट u. इनिशियल वेलोसिटी 20 मीटर पर सेकेंड. जब बॉल उसके हाथ में आ जाएगा तो फाइनल वेलोसिटी हो जाएगी 0. यहां पे भी 20 था, यहां पे भी 20 ही है, यहां पे भी 20 है. इनफैक्ट उसके हाथ को टच करने से जस्ट पहले भी इनिशियल वेलोसिटी इज 20 मीटर पर सेकेंड. ओके, विच मीन्स वी हैव टू ओनली लुक एट दिस सिनेरियो. पकड़ने के पहले और पकड़ने के बाद. पकड़ने के पहले वेलोसिटी 20 थी, पकड़ने के बाद 0 हो गई। अब ये 20 से 0 की जो जर्नी है, इफ इट हैपेंस इन 0.1 सेकेंड, फटाक अचानक 20 से 0 हो गया 0.1 सेकेंड, और मास 1 किलो है, व्हाट विल हैपन? F इज इक्वल टू ma, जो अभी डिराइव किया। m 1 kg mass of ball, a v minus u by t, 1 kg v 0 minus u 20 by t 0.1 minus 200 न्यूटन। इतना फोर्स क्रिएट होगा। माइनस, फोर्स इज अ वेक्टर क्वांटिटी, फोर्स के अंदर डायरेक्शन होता है, सो इट्स प्लस एंड माइनस, देयर टू डायरेक्शंस। उससे वो नेगेटिव फोर्स ऐसा कुछ नहीं है, रिटार्डेशन या स्लोइंग डाउन ऐसा कुछ नहीं है। फोर्स हैज डायरेक्शन एंड डायरेक्शन इज डिनोटेड बाय द साइन। तो फिलहाल साइन भूल जाओ। 200 न्यूटन ऑफ फोर्स इज अप्लाइड ऑन हिज हैंड्स। चमड़ी फट जाएगी, इट विल डैमेज, और बोन फ्रैक्चर हो सकता है। ऐसे कैसे? तो हर क्रिकेटर का हाथ थोड़ी फ्रैक्चर हो जाता है या स्किन फट जाती है, नहीं होती, बिकॉज देर इज अ टेक्निक। व्हाट इज द टेक्निक? इज जब वो कैच पकड़ता है, इवन विकेट कीपर जब बॉल पकड़ता है ग्लव्स के साथ, तो देखना वो अपने हाथ पीछे लेके जाता। आफ्टर कैचिंग ही टेक्स हिज हैंड्स बैक, ही डज नॉट जस्ट से ये पकड़ लिया। उससे क्या फर्क पड़ता है? उससे फर्क ये पड़ता है दैट इनिशियल वेलोसिटी वाज 20, but after catching the ball the hand is still moving, और फाइनल वेलोसिटी 0 थोड़ी देर बाद होती है। मतलब the time taken is approximately 1 second from full velocity to zero velocity, it takes 1 second। तो फोर्स पे क्या असर पड़ेगा? फोर्स इज इक्वल टू मास इनटू एक्सेलरेशन, mass 1 kg, acceleration is v minus u by t, 0 minus 20 upon 1 minus 20 न्यूटन। लुक एट द फोर्स, कितना ज्यादा फर्क है। 200 न्यूटन का 20 न्यूटन हो गया। देयरफॉर टाइम बढ़ाओ तो फोर्स कम हो जाता है, टाइम घटाओ तो फोर्स बढ़ जाता है। टाइम बढ़ाया 0.1 सेकेंड का 1 सेकेंड कर दिया तो फोर्स कम हो गया। आई विल गिव यू एन एग्जैक्ट रिवर्स सिचुएशन जहां पे टाइम घटा के फोर्स बढ़ाना है, टाइम घटा के फोर्स बढ़ाना है। एंड ऑल these questions can be asked in the exam. Cricketer catching the ball, why does it hurt? कराटे किड, कराटे में पत्थर तोड़ना सिखाते हैं। They teach you how to break the stone. कराटे वाले सब ना ऐसे दुबले पतले होते हैं, फिर भी पत्थर तोड़ देते हैं। What is the reason? हाथ को मारने का एक लिमिट होता है, हाउ मच वेलोसिटी यू कैन हिट द हैंड विथ। से मैक्सिमम लिमिट इज 20 मीटर पर सेकेंड, 20 मीटर पर सेकेंड। तो पहले हाथ ऊपर था, इनिशियल वेलोसिटी 0, फिर हाथ नीचे आया, फाइनल वेलोसिटी 20, पत्थर पे मारा। ये जो है इनिशियल वेलोसिटी 0 एंड फाइनल वेलोसिटी 20 के बीच में कितना टाइम लगाते हो उससे फर्क पड़ता है। इफ यू टेक 1 सेकेंड, हाउ मच फोर्स विल बी क्रिएटेड? फोर्स इज इक्वल टू मास इनटू एक्सेलरेशन। हाथ का मास 2 kg, सपोज। एक्सेलरेशन इज फाइनल माइनस इनिशियल अपॉन टाइम। यहां पे मैं कुछ बराबर। सो फाइनल माइनस इनिशियल अपॉन टाइम, टाइम क्या है? 1 सेकेंड। सो 2 into 20 minus 40 Newton. And 40 Newton force is not enough to break the stone. अगर पत्थर पे तुम 40 न्यूटन फोर्स अप्लाई करोगे तो पत्थर सामने उतना सेम फोर्स अप्लाई करेगा, वो टूटेगा नहीं। Because it is strong. Then how to break the stone? तुम्हारे हाथ का मास चेंज नहीं हो सकता, इट इज 2 kg, इनिशियल वेलोसिटी 0। तुम्हारा फाइनल वेलोसिटी भी जितना अचीव कर सकते हो उतना ही कर सकते हो, मीटर पर सेकेंड। बट व्हाट यू कैन ट्राई टू डू इज, इंस्टेड ऑफ टेकिंग 1 सेकेंड टू हिट, यू हिट फास्ट, यू टेक लेस टाइम। तो यहां पे टाइम घटाओ, 0.2 सेकेंड्स कर दो इंस्टेड ऑफ 1 सेकेंड। फिर देखो मजा। फोर्स इज इक्वल टू मास इनटू एक्सेलरेशन। मास 2 kg, acceleration is v minus u upon time, 2 into 20 upon 0.2, 100, 200 Newton force is applied. See the difference? That's the reason why a karate person can break the stone, because he is not applying extra force, he is not applying extra velocity. All he's doing is he's changing the momentum in a very short span of time. वो कम टाइम लगाता है, वो फास्ट है, इसलिए काम हो जाता है। दिस इज मैथमेटिकल फॉर्मुलेशन ऑफ सेकेंड लॉ ऑफ मोशन। सेकेंड लॉ ऑफ मोशन में चेंज ऑफ मोमेंटम मतलब फाइनल माइनस इनिशियल मोमेंटम। फाइनल मोमेंटम mv, इनिशियल mu, m कॉमन, v माइनस u। तो चेंज ऑफ मोमेंटम ये है, तो रेट ऑफ चेंज ऑफ मोमेंटम मतलब डिवाइड बाय t। एंड फोर्स इज अप्लाइड, फोर्स इज प्रोपोर्शनल टू रेट ऑफ चेंज ऑफ मोमेंटम, बट रेट ऑफ चेंज ऑफ मोमेंटम में v माइनस यू बाई टी बिकम्स a, और प्रोपोर्शनल जब इक्वल टू बनता है तो k आ जाता, वो बाय हार्ट कर लेना। Therefore f is equal to kma is the mathematical formula of second law of motion. Either you use my style or this style, both are same. By heart this, it's very important. This is the catch of a cricketer, which I have explained in tremendous detail, कि जब वो सीधा कैच पकड़ता है तो टाइम टेकन is less, therefore force created is more, therefore it can damage his hands. But when after catching he moves the hands downwards, the time taken is more, therefore the force created is less, therefore his hands will not get damaged. That was second law of motion. third law of motion and conservation of momentum we will do in the next lecture.
And inertia, we need to look at Newton's first law of motion again. Here it is. In simple words, this means that objects tend to keep on doing what they are doing. It is the natural tendency of every object to resist change in their state of motion. If they are at rest, they would prefer staying at rest, and if they are moving at a constant velocity, they would want to continue doing so. This tendency of objects is called nothing but inertia. It's the natural tendency of an object to resist change in its state of motion. Yes, you already knew what inertia is. And yes, Newton's first law of motion is also called the law of inertia. Do you think all objects have the same inertia? All objects resist changes to their state of motion, right? So all should have the same inertia, correct? Well, not really. Because inertia tells us how strong an object's tendency is to resist change in its state of motion. Think of it like this. There's a tiny brick kept on a table next to a relatively larger and a heavier brick. Which one do you think would be easier to push?
Without doubt, the tiny brick, correct?
Yes, but why is that? It's because the heavier brick's tendency to resist change in motion is more. The heavier the object, the more is its tendency to resist the change in motion. The more mass an object has, greater will be its inertia. So if we apply equal force to both these bricks, the tiny brick will move further as compared to the larger brick. The heavier brick has more inertia. How can we relate inertia and mass? Inertia is the tendency of an object to resist changes to its state of motion, and the mass of an object is the measure of its inertia. In the next part of this video, we will understand this relation with a few interesting examples. Remember the Newton's first law of motion. It says that an object will continue to do what it's doing unless acted upon by an unbalanced force or some net force. Now the important question is, what happens when there is net force acting on an object? That's precisely what the second law of motion will discuss. Do you remember understanding the first law of motion with a simple diagram? If the forces are balanced, the acceleration will be zero. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced. Only if the net force is zero. Now let's try to create a similar diagram for the second case. If the forces are unbalanced, then there will be acceleration. We saw that in the previous video. And now we come to the interesting part. Let me ask you a question and I'm sure you can answer it. On which two factors do you think the acceleration will depend on? I want you to tax your brain a bit. Let me repeat my question. On which two factors do you think will the acceleration depend on? Okay, let's say there's an object on a table. You apply a net force of 10 units on it. And then you apply a net force of 20 units on it. In which case do you think the acceleration will be more? Of course, the one in which the force was more. So we can say that one of the things the acceleration depends on is net force. If it's more, then more will be the acceleration. If it's less, then lesser will be the acceleration. Acceleration depends directly on the net force. Come on, now I want you to think about the second quantity the acceleration will depend on. Let's say there are two objects on the table. One has a mass of 3 kilograms and the other has a mass of 5 kilograms. Now, if you apply net force of 10 units to each of them, which one do you think will accelerate more? Surely it's the 3 kg one because it has lesser mass. Lesser the mass, more the acceleration. And more the mass, lesser the acceleration. Hence we can say that acceleration depends inversely on the object's mass. If you understand this concept well, then understanding the second law of motion will be very easy. Mathematically, it can be written like this. In simple terms, the acceleration is directly proportional to the net force applied and inversely proportional to the mass of the object. That's the second law. Or as more people understand it, like this. The net force is the product of mass and acceleration. With this, can you tell me the units of force? That should be easy. The standard unit of mass is kilograms, and that of acceleration is meters per second squared. So the unit of force is kilograms times meters per second squared. And this is what we call as Newton. 1 Newton is 1 kilogram times meters per second squared. So if the mass of the object is 10 kilograms and the acceleration is 10 meters per second squared, then the force will equal 100 newtons. We can say that 1 Newton is defined as the amount of force required to give a 1 kilogram mass and acceleration of 1 meter per second squared.
Newton's first law of motion. In our everyday life, we observe that effort is required to put a stationary object into motion or to stop a moving object. Have you ever wondered if a ball kicked on the ground would keep moving forever, or after some time would naturally stop moving? The ball will continue to move unless an object of force stops it. Here comes Newton's first law, which states a body continues to be in its state of rest or of uniform motion unless acted upon by an unbalanced external force. To understand Newton's first law, you need to understand what unbalanced force is. If you have seen a game of tug of war, you would have seen two teams pulling a rope in opposite directions. If the rope doesn't move, the forces applied by the teams are balanced forces as they are of equal magnitude in opposite direction. If one of the team applies greater force, it pulls the other team and the rope towards their side. In this case, the forces are unbalanced as the two forces are of unequal magnitudes in the opposite directions. If one of the team lets go of the rope, the opposite team falls backwards. This tendency to fall backwards despite letting go of the rope is due to inertia. That is, if an object is at rest, it tends to remain at rest, and if it is in motion, it tends to stay in motion. This property of an object is called its inertia. Inertia can be classified into three categories: inertia of rest, inertia of direction, inertia of motion. Certain experiences that we have while traveling in a bus can be explained on the basis of the law of inertia. When a passenger is standing in a stationary bus that suddenly moves, the movement pushes the passenger backward. Why does this happen? This is due to the inertia of rest experienced by the passenger in the upper part of his body. The body is at rest when the bus is at rest. When the bus starts, all of a sudden, the lower part of the body is in contact with the vehicle that started moving, whereas the upper part of the body continues to be at rest because of the inertia of rest. Inertia of rest is a tendency of a body to resist any change in its state of rest. What happens when a fast-moving bus negotiates a right-hand curve on the road? The passengers will tilt to the left. Inertia of direction is the tendency of a body to oppose any change in the direction of its motion. With the application of sharp brakes, the bus stops all of a sudden and the passengers tend to fall forward. This is due to inertia of motion experienced by the upper part of the body. When the bus is moving, the whole body of the passenger is in a state of motion. A sudden halt caused by the lower part of the passenger's body that is in contact with the bus comes to rest. However, the upper portion of the body remains in the state of motion due to the inertia of motion, causing the passenger to fall forward when the bus stops suddenly. Inertia of motion is the tendency of a body to resist a change in its state of uniform motion. Thus, Newton's first law is also called the law of inertia. Well, now this law should make sense. Do you understand why a ball on the ground after being kicked does not keep moving forever? The ball stops after some time due to the unbalanced external force applied by the ground in the opposite direction. Things to remember. Newton's first law of motion states that a body continues to be in its state of rest or of uniform motion unless acted upon by an unbalanced external force. Two unequal, oppositely exerted forces are called unbalanced forces. Newton's first law is also known as the law of inertia. The tendency of an object to continue its state of rest or of uniform motion in a straight line is called inertia. The three types of inertia are inertia of rest, inertia of motion, and inertia of direction.
Dr. Smith has an empty soda can and a full soda can. He is putting them both at the top of a ramp and is going to let go of them at the same time. What do you predict will happen? Did you get it right? This time Dr. Smith has 3 solid steel balls, a small one, a medium-sized one, and a large one placed at the top of the ramp. What do you predict will happen? We can see that acceleration is definitely present in these ramp experiments for all the objects rolled down the ramp. So that means with each object there is an unbalanced overall net force. Do you know what that force is? The force accelerating each object down the ramp is the object's weight. Weight is a force, and that is why the heaviest soda can or the heaviest steel ball always won the race of rolling down the ramp.
So Newton's first law of motion was that an object at rest wants to, everyone say, stay at rest. Stay at rest. An object in motion wants to stay in motion. Stay in motion. And essentially, that is Newton's first law, and that is the concept of inertia. Let me show you with what I call an inertia hat. Now this might look pretty funny, right? This doesn't really look like a hat. I made it out of a coat hanger and 2 tennis balls. And if I place the inertia hat on my head, does it have the inertia of being in motion or staying at rest? Staying at rest. Staying at rest. You might see just a little bit of movement because I'm talking, and there's slight movements with my head moving and with the air in the classroom moving, but for the most part this is staying still. Now watch what happens if I change the inertia by applying a force. So here's the force. Now what inertia does it have? Staying in motion or staying at rest? Staying in motion. And it's going around and around until the friction from the hanger hitting the top of my head slows it down. Now it's slowing down and it stops. Now I'm going to move. And did it change? Did it start moving? No. No, because there wasn't a force applied to it like when I moved it with my hand. There is friction happening, and because I'm not keeping my head perfectly still, there maybe was a little bit of a wobble, but it didn't really move. It mostly stayed still because I'm going to show you how to make your own inertia hat, which is great fun for seeing if you can spin around and have the hat stay still, or giving one side a little push and letting it orbit your head like a pair of planets. There we go. With a smoother push, it goes round and around like it's orbiting the sun. Lots of fun. So to make one, you just need a coat hanger and a little bit of patience because it is tricky to get it to balance like this. So the first thing you want to do is untwist your hanger so that you just have the wire. And you're going to try and get this as straight as you can. The straighter you get your hanger, the easier the next part is. So it doesn't need to be perfectly straight. I'm calling that good enough. Now we're going to bend it approximately in half. And once you get it bent in half, then you are going to take the ends and curve them down in an M shape. And you want the bottom part to be lower than your middle or your V. So we get them kind of heart-shaped, rounded. There we go with that end. And now the other end. And you can use pretty much anything to go on the end. So these tennis balls, wool dryer balls work well. I've got this one that I made with squeaky toys from the dollar store and little styrofoam eggs. These are a little bit too light. They don't work quite as well as the tennis balls, but they're a little more comfortable on the top of your head when they're lighter, so plus or minus depending on what you use. You can see how this hat is not staying up straight, it's tipping forward, and that means that it's not in line. So I could try to adjust it by pulling something back a little bit, and then just balance it on your hand and see if that looks better. And it won't take too long for you to figure out that minor tweaks make a big difference. Even it out. Whoa! And see, all of a sudden I did something wonky, and instead of the hat balancing upright now, it's balancing in that weird, crazy angle, and we don't want that because it's not going to stay on my head well if it's not balancing upright. So I need to try and tweak it back, see if that was enough. And there we go. Now we're almost upright again. Maybe. Oh, yes! I want to tell you something important about inertia. Mass matters when it comes to inertia. The amount of stuff that you have, the amount of weight, is going to make a really big difference. I'm going to be applying about the same amount of force each time I flick my finger. And is it a whole lot of force or not that much, right? No. Now, here is an empty water bottle. It's really light. Here is a half full water bottle. And here is a water bottle that's almost all the way full and is a lot heavier. Watch what happens to these water bottles when I flick them. So, the light one just fell right over, right? That one tipped forward, but then went immediately right back. And that one I just hurt my finger, but it really doesn't move very much at all. And that's because this one has more weight. Everyone say inertia. Inertia. It has more inertia. 1, 2, 3. So, which one moved the most? This one did, right? And it's because it is light and it doesn't have as much inertia. And so when I pulled it out, this one tipped over. Did you see any difference between how these ones behaved?
No.
3.
What?
This was interesting. We had, just like Goldilocks and the Three Bears, we have too light, too heavy, and just right. Now, right now, these Easter eggs, which are full of Play-Doh, so that makes them kind of heavy, and things that are heavy have more inertia. These Easter eggs, are they at rest or are they moving?
Rest.
They're at rest, so they have the inertia of wanting to stay at rest. And if I apply a force to them, they'll move. But if I don't apply a force to the egg, but instead apply a force to the pan, then I should be able to get the egg to land in the cup. You guys ready? 1, 2, 3.
Oh my god.
Yeah, we'll do 1, 2, 3, go. Woo! Round of applause for the boys. They're amazing. There's another variation on this we're going to do now with bunnies. So, and this time, I would like to have 2 students come up. And 1, 2, 3.
Wow.
And now this time I'm going to say 1, 2, 3, and it'll be like slow motion pulling back. And let's see what happens, okay? 1, 2, 3, slowly go back. Very different, right? If I just give this string a tug and get them started, once part of this string of beads has inertia, it starts moving and it wants to stay in motion. It wants to keep moving and it pulls the rest of the beads out. But if you watch closely, you'll see something really cool. When they come out, they don't just come over the top like this, they actually lift up and over the edge. You guys ready? Happens pretty fast. I'll put them in and we'll do it one more time. You can buy inertia beads online, but you don't need to. You can make your own by taking party necklaces, cutting them apart, and then fixing them together with duct tape. This is the 47th string in my homemade inertia beads, and when you put them in the container, you just need to be sure to put them in bit by bit, the same way that you want them to come out. So let's give them a tug and see how they do. Not bad. When you put them back in the container, it's important to feed them in the same way that they come out. Oh, and then just have the egg. Sure, we can try that. 3.
Can we try the bunny on the toilet paper roll?
The bunny on the toilet paper roll? Sure. That would be a good one to do next.
Oh, I don't want to.